Hey guys, I want to welcome you to our first lecture video for Chem 115. In this video, I want to revisit the topic of calculating the pH for weak monoprotic acids and weak monoprotic bases. We are going to look at a couple of typical examples, and then we are going to work through several examples where there are some various changes. I do want to note that this lecture video will be broken into two videos. So after you watch the first part, feel free to take a break and watch the second part. Also, if you already feel comfortable with this topic, I encourage you to pause the video when you see the questions and work them out on your own. After you guys have finished working them out, you can go ahead and fast forward the video to check your work and check your answer. All right, so let's go ahead and get started. And so our first problem that we're going to work on is a typical example of weak monoprotic acids. So reading the question, what is the pH of a 0.142 molar benzoic acid solution? And here in this case, I've given you two ways to write benzoic acid. It's HC6H5CO2 or C6H5COOH. When you get into organic chemistry, this is something that you guys are going to come across constantly. So benzoic acid is an organic acid. It's an organic compound. And so you guys are, for those who are moving on to organic chemistry, you guys are going to learn why it's written in two ways. Nonetheless, let's go ahead and continue reading the problem. So the Ka for benzoic acid is 6.52 times 10 to the negative 5 at 25 degrees Celsius. So we're going to go ahead and address the first question. We're going to figure out the pH of this specific molarity of benzoic acid. And then there's a couple of follow-up questions that we're going to address. What is the percent ionization? And what is the pOH and the concentration of OH minus? And so this bracket around this hydroxide is representing molarity. Okay, cool. So what I'm going to do is I'm going to go ahead and highlight the main important information. And so I have a 0.142 molar benzoic acid solution, and the value for my Ka, or my acid ionization constant, is 6.52 times 10 to the negative 5 at 25 degrees Celsius. And so whenever you guys are working through these types of problems, the temperature doesn't really play a strong role in terms of like inputting it into a formula, so to speak. It's just letting us know that this is that at that specific temperature, the acid ionization constant, which is an equilibrium constant, is 6.52 times 10 to the negative 5. Also, since we're at 25 degrees Celsius, if we need to use it, since we're at this specific temperature, we know that the Kw, the ionization constant for water, is going to be 1.008 times 10 to the negative 14. And so it's just reminding us that we can go ahead and use some of these values if we are at 25 degrees Celsius. And if we're not at 25 degrees Celsius, we will have to look up the value of Kw. Okay. All right, and so the question is asking us to determine the pH. All right, well, what is the pH of this solution? And so if you guys recall from the last time we met a couple weeks ago, the pH is representing the concentration of hydrogen ions, specifically at equilibrium. And so if we can figure out what the concentration of these protons are at equilibrium, then we can go ahead and apply the equation pH is equal to negative log of H plus to figure out what the pH of that solution is. And so just always keep in mind that pH is calculating those protons at equilibrium. And so upon realizing that lets us know that we probably have to build an ice table. And so the ice table kind of organizes our values so that we can figure out the equilibrium concentration for each part in that chemical formula or in that chemical equation. And so part of building our ice table is to be able to write a balanced chemical equation. So let's go ahead and do that first. And so it looks like benzoic acid has two chemical formulas. I'm just going to go ahead and use the first one that I see. And I'll go ahead and talk about the second one in just a second. And so just imagine that we are going to take HC6, H5, CO2. We're going to take this this chemical formula for benzoic acid, and then we're just going to go ahead and place it in water. We're going to allow this compound to dissolve as much as it can, and then we're going to go ahead and take a pH meter, stick it into the solution, and read the pH. And so that's the steps that we would do in lab if we were actually trying to determine the pH physically. But for this type of scenario, we can go ahead and determine or calculate the pH without the use of a pH meter. And so for us to do so, we're going to have to look at this chemical formula and figure out what the ionizable hydrogen is. And so here there are two sources of hydrogen. Here there's a hydrogen right in the front, and there's a hydrogen right in the middle. There's 5 hydrogens right in the middle. And so when you guys are trying to write a balanced chemical formula, you want to be able to ionize your ionizable hydrogen. And if your chemical formula is written in this fashion, and this is probably coming from the first semester of general chemistry, the first element that you typically see is the cation. And anything else after the cation is going to be the anion. And so in this case, since this hydrogen is our cation, that's going to be our ionizable hydrogen. So what this means is that when we're writing a balanced chemical equation, we're simply going to separate that first hydrogen from the rest of the compound. And so I'm going to go ahead and write the physical states of matter because we're putting all of this stuff in water, so it's going to be aqueous. And what we're left over is C6, H5, oops, CO2. Now, since we separated the hydrogen from the rest of the compound, this is going to be benzoate. Benzoate is going to get that negative charge. So remember that cations are always positive in charge and anions are always negative in charge. And so when they're placed together in a chemical formula, their charges kind of balance and they kind of cancel. However, when you separate them, their original charges needs to be written. And so since the only thing that we've done is since the only thing that we've done, I'm just going to erase some of this stuff. Since the only thing that we've done is separated this hydrogen from the rest of the compound, when we're trying to balance a chemical equation, this is going to be typically a 1-to-1-to-1-to-1 ratio. Now, if you guys are using the other chemical formula for benzoic acid, the ionizable hydrogen in this case is going to be found at the very end. Okay. All right, so now that we have a balanced chemical formula, what we're going to do is we're going to write an ice table. And so the ice table is going to represent the initial concentration of each and every single one of these chemical compounds. the C in ice in the ice table is going to represent the change. And last but not least, the E is going to represent the equilibrium concentration. So this is typically what we're interested in if we're trying to figure out the pH of the system. And so I'm just going to go ahead and make this table right here. Oops. And so since the physical state of matter for every single one of our compounds is aqueous, that means that all of these chemical species needs to be included in our mass action expression. And so let's go ahead and take a look at I, or the initial concentration. And so the initial concentration of benzoic acid is this 0.142 molar concentration. And so we're just going to go ahead and put that down, so 0.142 molar. Now in the problem, it didn't really indicate what the initial concentration of hydrogen ion is, or that of benzoate. And so we're just going to go ahead and put a horizontal line to represent that nothing is there. Now, when we're looking at the change, or C, we need to understand the chemistry of our chemical compound. And so if you look at our Ka value is something, something, something times 10 to the negative 5. So much like what we learned in our equilibrium chapter, if your equilibrium constant, whether it be Ka, Kw, Kc, Kb, is far, far less than 1, then we know that in this specific scenario, let me bring it back to this specific scenario, then we can conclude that this compound is a weak acid. And so that's basically telling you that at equilibrium, there's going to be only a few products that's formed, and most of it is still going to be a reactant. And so for the change for a weak acid, and also since our Ka value is far, far less than 1, this is telling us that benzoic acid is a weak acid. And so if our Ka value is far, far greater than 1, then that's telling you that that specific compound is going to be a strong acid or a strong base. And so for weak acids, we don't really know how much is going to ionize. And so we're just going to go ahead and write negative 1x. So this 1 is coming from the coefficient. And we know that if we're consuming benzoic acid, some amount of benzoic acid, we're also going to produce some amount of hydrogen ions and some amount of benzoate ions. So we're just going to go ahead and put in plus 1x and plus 1x. Okay. Now when we calculate our equilibrium, we are going to basically add downwards. So then this is going to be 0.142 minus 1x, or just x. So please make sure that it's always the initial concentration minus the change. Okay. And then that's always going to equal your equilibrium concentration. And so when we're adding down in this column, it's going to be 0 plus 1x, or just plus 1x. And same thing down here, or same thing for the last column. Okay. And so now that we have, now that we've built our ice table, we can see that if we can figure out what this x is for this hydrogen ion, we can go ahead and plug that into this space, if you will, to figure out the pH of the solution. Okay. And so our goal is to figure out what the value of this x is. And so to do that, what we're going to do is we're going to write a mass action expression for this chemical equation. And so since this chemical equation is describing the ionization of the acid, we're going to go ahead and represent that with Ka, right? And so whenever you're ionizing your hydrogen ion, whenever you're ionizing your hydrogen from its compound, you're describing the separation of it. And so therefore, it's going to be represented by Ka, the ionization constant of the acid. And so Ka is going to equal, let me just scroll up here, the concentration of hydrogen ion at equilibrium raised to the first power. And we're raising it to the first power because that is the coefficient. And then we're going to go ahead and multiply that by the concentration of benzoate, so C6H5CO2 with a negative charge raised to the first power. And then we're going to go ahead and divide that by our reactant. So here in this case, it's going to be the concentration at equilibrium, So concentration of HC6H5CO2. Once again, we need to remember that all of these values are going to be at equilibrium. So now that we've written the mass action expression, what we're going to do is we are going to plug in what we've written down to what they represent. And so since the benzoate is represented at equilibrium with just the variable x, we're going to go ahead and plug in x in place of that chemical formula. And so the same thing can be said about this hydrogen ion. Since at equilibrium is just being represented as plus 1x, we can just go ahead and put in x. And then last but not least, for the benzoic acid, the equilibrium expression for benzoic acid is going to be 0.142 minus x. So we're going to go ahead and plug that down here. Okay. And so if I clean up my work, I'm going to get x raised to the first power times this by x raised to the first power, divide this by 0.142 minus x raised to the first power. Oops, I forgot to put that. And so all of these exponents, I'm grabbing it from the coefficient. So notice that it's 1 to 1 to 1. And so therefore my exponent is 1 to 1 to 1. And so these coefficients are being represented twice. They're being represented as the coefficient in the change, and they're also being represented as the exponent in our mass action expression. So please don't forget that. Now, finally, the Ka value is going to be 6.52 times 10 to the negative 5. All right. So if we simplify our equation, we're going to get 6.52 times 10 to the negative 5 equals to x squared over 0.142 minus x. And so a couple things, I need to remind you guys that Ka is unitless. Ka is a ratio of the rate of the forward and the rate of the reverse. And so the units for rate will cancel. All right. And so looking at what we have down here, if we perform algebra on it, what we're going to do, what we are going to get is a quadratic equation. And so a quadratic equation forces us to use the quadratic formula. And so we want to avoid that as much as possible, just because there's a lot of algebra and a lot of steps that comes with it. And if there's just a lot of algebra and a lot of steps, you're more prone to getting errors. And so what we want to do is we want to work smartly. And we're going to determine if we actually need the bottom x. So can we ignore this bottom x, or does it actually have to be present in this mass action expression? And so remember that x is representative of the change. And so if this x, this change, is significant with respect to the initial concentration, then that means that we must keep that x there. However, if this x, if the change is very minuscule, it's very minute, such that it won't really affect the value of the initial concentration too much, then we can go ahead and ignore it. And we can go ahead and answer that question by making sure, by determining if this statement is correct. The initial concentration must be far greater than the value of the equilibrium constant that's given to us in the problem. In this case, it's going to be Ka times 100. And so if we can go ahead and prove that this specific statement is true, then we can go ahead and ignore this bottom x. And so our initial concentration is going to be 0.142 molar. So I'm going to go ahead and put in 0.142 molar at the very top. And so my Ka value is going to be 6.52 times 10 to the negative 5. And then this is going to be times 100. So I'm kind of working upwards here. And so if I have 0.142, so 0.142 is going to stay the same. We don't need to change that. However, if you multiply 100 by this scientific notation, what we get is 6.52 times 10 to the negative 3. And if we express that as a decimal so that we can compare it to this decimal, it's going to be 0.00652. Okay. And so I went ahead and multiplied both of these two values together, and it would give me that answer. Now, let's go ahead and look at the result of this statement. Is 0.142 far greater than 0.00652? And the answer is yes, it is far greater. It's about 2 orders of magnitude greater. So if it is, I'm sorry, 1, 2, 3, 1. Yeah, it is 2 orders of magnitude greater. And so if you did conclude, if you did say yes, then that means that you can ignore this bottom x. And so what this is telling us is that this change is not going to affect the initial concentration all too much. However, you don't want to exclude the x at the very top, because this x is representing how much product that we're going to get. So basically anything above 0, right? So if I scroll upwards, notice that we have no initial concentration of hydrogen and no initial concentration of the benzoate. And so anything above 0 is significant, right? And so that's why you don't want to ignore the x in the numerator. All right. And so if we ignore the x in the denominator, we're just going to get 6.52 times 10 to the negative 5, which is equal to x squared over 0.142. And so by removing that x in the denominator, it really simplifies our calculation. And all we're going to do is we're going to multiply 0.142 to the other side. And so this is going to be 6.52 times 10 to the negative 5. I'm going to put that in parentheses, times that by 0.142, which equals to x squared. And so you guys can go ahead and multiply this in your calculator, but I'm just going to push forward. To get rid of this square, I'm going to take the square root of both sides. And so the value of x is going to be equal to the square root of the product of 6.52 times 10 to the negative 5 and 0.142. And so if you guys calculate that out, you guys will get 0.00304. And we want to make sure that we have 3 sig figs, because there are 3 sig figs in our calculation. Awesome. So we did it. We solved for x, but just solving for x doesn't mean that we've solved the entire problem completely. Remember that x just represents the change. And so what we're going to do is we're going to revisit our ICE table, and we're going to plug in that change into wherever we see x. And so I'm going to go ahead and just kind of copy all of this. Actually, you know what? Let me just copy everything. I think it might be easier if I just rewrote all of this, because I will have to erase some of this stuff, but let's work with it. Okay. So I'm going to erase some of this stuff here so it's less busy. All right, that looks good enough. So now that we've figured out x, or the change, what we're going to do is we're going to plug in this value into everything that every place where we see x. Now you have to keep in mind what we're trying to really address. The question is asking us to determine the pH of the solution. And so the pH of the solution can be calculated by using this formula. pH is equal to negative log of the concentration of H plus, specifically at equilibrium. So really the only thing that we care about is this guy that's in yellow. And so notice that the expression for the equilibrium concentration of hydrogen is just plus 1x, or just x. And so therefore this value is also representing the concentration, the equilibrium concentration of hydrogen ion. And so the concentration of this hydrogen ion at equilibrium is going to be equal to 0.00304. And since now we're talking about concentration, we're going to go ahead and tack in the unit molarity. So please don't forget that. Awesome. And so now that we have the equilibrium concentration of hydrogen ion, what we're going to do is we're going to plug this value right inside that bracket to determine the pH of the solution. And so when you plug that into your calculator, you guys are going to get 2.517. Now let's go ahead and quickly talk about Sig Figs for pH. If you guys are working with, when you guys take the negative log of something, notice how that there's 3 significant figures in this value. So when you take the negative log of that value, you guys need to report 3 places after the decimal, or 3 decimal places. So I'm just going to go ahead and write 3 dp to represent decimal places. And so the whole number in your pH, it's not significant. That's actually representing the exponent in your scientific notation. And so anything that comes after the decimal for pH is going to represent the correct number of significant figures. Awesome. So this is our final answer. So the pH of the solution is 2.517. And since the pH is less than 7, we can say that this solution is acidic. Cool. So let's go ahead and look at what other questions we need to address. And so we need to calculate the percent ionization, and we need to determine what's the pOH and what the concentration of the OH minus is, or the hydroxide ions. And so I'm going to go ahead and solve for the pOH and the concentration of hydroxide ions first, just because I'm already at pH. And so to do that, we're going to go ahead and use this relationship. The pH plus pOH is equal to 14. And so if I plug in my pH value, that's 2.517. And if I represent the pOH as like a variable, then I can just go ahead and subtract 2.517 on both sides. And therefore my pOH is going to be 11.483. Once again, you don't want to lose the number of decimal places, right? We want to be precise with our values. All right, and so now that we figured out the pOH, we're going to figure out the concentration of the hydroxide ion. And so, if you guys recall, the pOH is equal to the negative log of the concentration of the hydroxide ion. And once again, that's always at equilibrium. And so to solve for the bracket OH, we're going to go ahead and move this negative to the other side. So it's negative pOH is equal to the log of the concentration of OH minus. And so to get rid of the log, we're going to go ahead and raise it to the base 10 power on both sides. And so that's going to cancel the log. So just think of logs and base 10s like an operation, like multiplication and division. So they're simply opposites of each other. And so to cancel out a log, you need to raise it to the base 10. And what we have left over is a specific equation. So the concentration of OH minus at equilibrium is equal to 10 to the negative pOH. And so if you simply plug in the value for the pOH in this chemical, or in this formula, we'll be able to get the concentration of our OH. So it's going to be 10 to the negative 11.483. It's going to be OH minus at equilibrium. And so if you plug that into your calculator, you guys are going to type in second log. That's typically how it is for most calculators. If you guys are using calculators that are not Casio or not TI calculators, you guys just need to figure out where that function is. But for most calculators, TIs and Casios, you guys are going to type in or push in second and then log. And that should give you this base 10 function. And so the concentration of OH minus at equilibrium is going to be 3.29 times 10 to the negative 12. And since we're talking about concentration, we need to, I'm going to move this over here. We need to write in the correct unit for concentration. In this case, it's going to be molarity. Now, notice that there are 3 decimal places in our POH, so therefore we need to record 3 sig figs. And so when you guys are typing this answer into your calculator, just make sure that you guys are rounding correctly. And so our final answer is going to be 3.29 times 10 to the negative 12. And that is the concentration of the hydroxide ions in solution. So notice that this is times 10 to the negative 12. That's a really, really, really low amount. And so since there's not a lot of hydroxide solution, the solution cannot be basic. In this case, it's going to be acidic. And so if you look at the concentration of RH+, it's 0.00304, which is much higher than something that's times 10 to the negative 12. All right. So the last thing that we're going to solve for is the percent ionization. So the percent ionization it's equal to the change divided this by the initial concentration times 100. Okay. And so the initial concentration, we're going to have to just kind of scroll up a little bit. So the initial concentration is going to be 0.142. And so that's going to be in the denominator to determine the percent ionization. Just think of the initial concentration as like the whole, right? Whenever you take a percent of something, it's always part over whole. And so since the initial concentration is representing the whole, which is in the denominator, the numerator is going to represent the part. And so that's going to represent the change. And so here in this case, the change is going to be the value for x that we solved for. And so the change is going to be 0.00304. And so we're going to put in 0.00304, divide this by the initial concentration, which is going to be 0.142. And then we're going to go ahead and multiply that by 100 because we want to express this in terms of percent. And so if you guys type this into your calculator, plug it in, press equals, the percent that we are going to get is 2.14. And so this is letting us know that this is how much of the total population of benzoic acid, if you will. So 0.142 molar, that's equal to 0.142 moles per 1 liter. And so only 2.14% of the total number of moles of benzoic acid is actually ionizing to form the product. The rest is going to be, it's just going to stay as a reactant. Cool. And so hopefully going through this problem just kind of brings forward in your mind on what we talked about 2 weeks ago. Okay. Cool. So let's go ahead and work through another problem. This time, instead of working with monoprotic acids, we're going to work with monoprotic bases, and we're going to see how they're the same or how they're different from the first problem. And so for number 2, we want to determine once again the pH. So let me highlight this. When 0.734 moles of methylamine is dissolved to make a 2-liter solution, the base ionization constant for methylamine is 4.40 times 10 to the negative 4 at 25 degrees Celsius. And so after we determine the pH, we're going to determine the percent ionization. And we're going to determine the pOH and the concentration of hydroxide ions. Now, since we're trying to determine the pH of the solution, once again, pH is always measured at equilibrium, or the solution has already reached equilibrium by the time we take the pH of it. And so, since we want to determine the pH, this should bring in some things to the front of your mind. You want to determine essentially the concentration of hydrogen ions at equilibrium. And so for us to do that, we need our mass action expression, or equilibrium law. We also need an ice table. But for us to be able to develop an ice table in the mass action expression, we need to write a balanced chemical formula. I'm sorry, balanced chemical equation. Okay, so those are these are the type of items that needs to be kind of brought out when the question asks, what is the pH of this system? All right, since so we're going to go ahead and work backwards. So this is the first thing that we need to figure out. This is the second thing that we need to figure out. This is the third thing that we need to figure out before we can even figure out what the equilibrium concentration is. And then once we figure out the equilibrium concentration of hydrogen ion, then we're going to worry about the pH. So we're going to calculate the pH. So our compound in this case is going to be methylamine. So methylamine is CH3NH2. And so this problem already told you that it's going to be a base, right? So here the base ionization constant for methylamine is 4.40 times 10 to the negative 4. And so whenever you guys are writing your chemical formula for monoprotic bases, or bases just in general, you guys need to write in water. And so if you look at the structure of this base, typically when we think of bases, we're thinking of hydroxide ions. But hydroxide ions is nowhere found in methylamine. And so the source of those hydroxide ions is actually going to come from water. And so this is the reason why, so this is the reason why we need to include water in our chemical equation. And so the physical state of matter for methylamine is going to be aqueous because we're dissolving it in solution. And water, since that's a pure substance, that's going to be liquid in physical state of matter. I'm actually going to rewrite water in a different way, just so you guys can see what's happening. And so I'm going to write water as HOH. Okay? And once again, this is liquid in form. Now, the mechanism for this reaction, and you guys are going to learn mechanisms in organic chemistry. So there is a lone pair on this nitrogen if you draw its Lewis structure. And so this lone pair, it's going to quote-unquote attack this hydrogen. And the covalent bond that's between the hydrogen and the oxygen is going to go to oxygen. So it's nucleophile to electrophile. I tossed up some organic chemistry terms. And so if we're trying to use our terminology for this specific chapter, methylamine is going to act as a Lewis base. And the water is going to act as a Lewis acid. And so here in this case, protons are not specifically transferred. It's going to be a lone pair. All right, and so when we write the products for this chemical reaction, we're going to get CH3, NH3. So here in this case, since we're taking this hydrogen and we're placing it on the nitrogen of methylamine, we're going to get 3 hydrogens instead of 2. And so if we're absorbing an extra hydrogen, we're absorbing an extra proton. And if you recall from general chemistry, from first semester general chemistry, a proton is positive in charge. And so if we're absorbing an extra hydrogen, we're taking on an extra positive charge. This is going to be aqueous. And the result that we get is OH minus. Okay. And so, methylamine acts to increase the concentration of hydroxide ion by removing one of the hydrogens from water and placing it upon itself. And so CH3NH3, this is going to be the conjugate acid to this Lewis base. Okay. Cool. So now that we have a balanced chemical equation, and once again, everything is 1 to 1 to 1 to 1, just because we're just like dissociating things. We're not really adding on to the chemical equations. We're just separating it. So the ratio is just 1 to 1 to 1 to 1. Now, if you guys want to check my work, feel free to pause the video and just count the number of carbons on both sides, count the number of hydrogens on both sides, count the number of nitrogens on both sides, count the number of oxygens on both sides, and you'll see that it's a balanced chemical equation as written. And so now that we wrote the balanced chemical equation, we are going to go ahead and write our ice table. Oh, actually, you know what? Let me take it back. Not that I did anything wrong or anything like that, but there's another point that I do want to make. So notice that our reactant is a Lewis base. And so what we're describing in this chemical reaction is the ionization of this hydrogen by, the attack on the Lewis base, so to speak. And so here in this case, in the forward direction, we're describing the ionization of the base. And so this is representing Kb, not Ka. Another way to think about it is that we're starting with a base on the reactant side, and so therefore our equilibrium constant is describing Kb, not Ka. All right, so now that I've written ICE, let's go ahead and determine the initial concentration. And so the initial concentration, right now it's in moles, not molarity. And so we need to figure out the initial concentration by dividing both of these two values. So please recall that molarity, or capital M, is moles of the solute divided by the liter, moles per liter of solution. And so we're going to go ahead and take 0.734, and then we're going to divide this by 2.00 moles and liter. And if you divide those two values, what we get is 0.367 molar concentration. And so the initial concentration for our methylamine is going to be 0.367 molar. So let's go ahead and look at the change. So to determine whether or not our change is going to be, minus x or the initial concentration, we need to look at the magnitude of our equilibrium constant. And so here in this case, since the base ionization constant is times 10 to the negative 4, that's far, far less than 1. So this is telling us that methylamine is a weak base. And if we have a weak base, then the change is going to be represented by minus x, minus 1x, because the coefficient is 1. Just because we don't know how much of that weak base is actually going to ionize. If it was a strong base, then we know that's 100% ionization, and so therefore our change would be equal to the initial concentration. But here in this case, since it's a weak base, we don't really know. That's what we're trying to figure out. And so for water, since it's liquid in state, we're just going to go ahead and ignore everything. If you recall from the equilibrium chapter, anything that has a physical state of liquid and solid is just completely ignored in the mass action expression. And so the problem didn't really give us initial concentration of the conjugate acid, nor did it give us the initial concentration of the hydroxide. And so the only thing that we're going to fill in for the change with respect to the conjugate acid and the hydroxide is plus 1x. Okay, so the 1, once again, is coming from the coefficient of the acidic form of methylamine, the conjugate acid. And it's going to be plus 1x for this hydroxide. Now, for equilibrium, remember we're just going to add downward. And so it's going to be 0.367 minus 1x. And then it's going to be plus x and plus x, plus 1x plus 1x. Cool. So in our solution map, we have the balanced chemical equation, we have our ice table, so the next thing that we need to work on is our mass action expression. And so our mass action expression in this case is going to be representative of Kb, the ionization of the base. And so Kb is going to equal to the concentration of the product. So in this case, it's a conjugate acid of the methylamine. So it's going to be CH3 NH2, or NH3, I apologize, raised to the first power, because the coefficient is 1, times this by the concentration of hydroxide ion raised to the first power, then divide this by the concentration of methylamine raised to the first power. Okay. And so now that we have our mass action expression, we're just going to plug in everything from our equilibrium to, let me just write this down. So it's equilibrium. We're going to plug in all of our equilibrium expressions into their respective place in the mass action expression. And so this is going to be x, this is going to be x, and this whole thing is going to go at the bottom. And so Kb is 4.40 times 10 to the negative 4. So 4.40 times 10 to the negative 4. And that's going to equal to x raised to the first power times this by x raised to the first power over 0.367 minus 1x. Okay. And so if we simplify our work, we get x squared over 0.367 minus 1x. And so if you leave everything as is, once again, since we have x squared and we have an x, if you perform algebra and move everything to one side, you get a quadratic. And so we don't really want to use the quadratic formula if we don't have to. And so once again, we're going to assess whether or not we need the x in the denominator. Can we ignore this, or should we leave it and perform the quadratic equation? And to answer this question, we're going to see if the statement is true or false. So the initial concentration should be far, far greater than the the value for the equilibrium constant, in this case, since this is a base, we're going to go ahead and put in Kb times 100. And so you really want to make sure that the magnitude, the difference in magnitude is at least 2 and above. If the order of magnitude is 1 between the initial concentration and Kb, you guys will probably have to perform the quadratic equation. And so the initial concentration is going to be 0.367. And the Kb value is going to be 4.40 times 10 to the negative 4 times this by 100. And so I'm going to work upwards here. 0.367, far greater than 4.40 times 10 to the negative 2. Okay. And so here in this case, the statement is true. 0.367 is far greater than 0.440 times 10 to the negative 2. I'm going to go ahead and expand this as a decimal, so 0.0440. So this value is far greater than this value. And so that lets us know that we can ignore this. Can we ignore it? Yes, we can. And so we're going to go ahead and put in 4.40 times 10 to the negative 4. That's going to equal to x squared over 0.367. And so once again, if you perform the algebra, we're going to go ahead and get 4.40 times 10 to the negative 4 times this by 0.367. So we're multiplying 0.367 to the other side, and that's going to equal our x squared. And so to get rid of this to get rid of this square, we're going to take the square root of both sides. And when we plug all of that into our calculator, everything that I have here in parentheses, we are going to get 1.6148 times 10 to the negative 4. There's probably a whole bunch of digits after that 8, but I just chose to write this. I just chose to write this value. Oh, I'm sorry. Wrong number. So that's going to be 1.27 times 10 to the negative 2. That previous number that I wrote was the result of the product between these two. But once you take the square root of what I just erased, you guys will get 1.27 times 10 to the negative 2. Awesome. So once again, we finally solved for x. And so this x is going to represent our change. And so we're going to go ahead and basically plug everything into this ice table here. And so, yes, I don't want to write this over again. Oops. So I'm just going to go ahead and copy it. Okay. And we're just going to erase some stuff here. Sure. That works. All right. So now that we've figured out the change, we're going to go ahead and plug that value into all of these x's. But once again, we want to work smart. And so what we are trying to really address is, what we're trying to really determine is the pH of this solution. And to get the pH of the solution, we need to figure out the concentration of H plus at equilibrium. And so if you look at the identity of the compounds in our chemical formula, we don't really see hydrogen ions. We see our methylamine, we see water, we see the conjugate acid of methylamine, and we see hydroxide. And so we're kind of like in this stump, like, okay, well, if none of it is H+, then how can we solve for H+? Well, if you guys recall the relationship between acids and bases, we can still figure out the concentration of H+ if we determine the concentration of OH at equilibrium. And so we're going to go ahead and use specifically, I should not have highlighted that. We're going to go ahead and specifically use this equilibrium concentration, or this equilibrium expression, this X, to represent the equilibrium concentration of the hydroxide ions. And then from there, we're going to figure out the equilibrium concentration of hydrogen ions using one of these formulas that we discussed a couple weeks ago. And so for now, since X is equal to 1.27 times 10 to the negative 2, that's going to equal to the concentration of OH minus. And so the concentration of OH minus is 1.27 times 10 to the negative 2 molar. Okay. So to figure out the concentration of H+, we're going to use this relationship. So the concentration of H+ times this by the concentration of OH, which is equal to 1.008 times 10 to the negative 14. And so here in this case, I'm just going to show all the significant digits for kW. All right, so we're going to go ahead and, actually that's not kW. Anyways, so we're going to go ahead and plug in, or we're going to go ahead and solve for H+, times this by the concentration of hydroxide, which is, in this case, is 1.27 times 10 to the negative 2. And so that's going to equal to 1.008 times 10 to the negative 14. And when you solve for X, or in this case H+, that's going to be hold on real quick. Let me calculate that. Where's my calculator? So here in this case, the concentration of H+ is going to be 7.94, so I'm rounding it to 3 Sig Figs, times 10 to the negative 13. And so now that we have the concentration of H+, we can go ahead and take the negative log of this number to get the pH. So pH is equal to negative log of 7.94 times 10 to the negative 13. All right. And so the pH that I'm getting here in this case is going to be 12. Since there are 3 significant digits in my concentration, I need to report 3 places after the decimal. So 12.100. Okay. And so we want to include the zeros. We don't want to exclude it. Once again, we're after precision of our values. Now to determine the pOH, we're just going to go ahead and take the negative log of this value. And so if you guys plug that into your calculator, the negative log of 1.27 times 10 to the negative 2, the pOH that you guys are going to get is 1.8996. Or another way for you guys to figure out the pOH, instead of taking the negative log, you guys can go ahead and get pH plus pOH is equal to 14. And so if you have 12.100 and then you have pOH, you can go ahead and solve for pOH. Okay. So it's going to be 14 minus 12.100. Okay. And so here in this case, I get a calculator answer of 1.89965681. And so here, since I have 3 places after the decimal, I need to report 3 places after the decimal. And so this 6 is going to round up that 9, and it's going to round up this 9 as well. So overall, we have 1.900. Okay. And that would be the pOH. Cool. So the last thing that we need to determine is the percent ionization. And so please remember that the percent ionization is equal to the change over the initial concentration times this by 100. And so the initial concentration, if we look at our ice table, is going to be 0.367 molar. And the change, which corresponds to x, is going to be 0.12 or 1.27 times 10 to the negative 2. Times this by 100. And so if you guys plug this into your calculator, you guys are going to get a value that is 3.46%. And so once again, this is telling you that if you have 0.367 moles per liter of methylamine, only 3.46% of this total number of moles of methylamine will ionize to form the products. Cool. And so that pretty much finishes this problem. So the main point of this problem is to be able to be able to determine the pH if we're starting off from a weak base instead of a weak acid. Okay. So just some points, some differences. Since in our product we have hydroxide ions and not H+ ions, we do have to take an extra step once we solved for X. We have to determine the concentration of this hydrogen ion by using this specific formula. All right. So we're going to go ahead and start varying the scenarios. So we're still going to be using the same idea of determining the pH for either a weak base or a weak acid, but we're just going to add some differences here and there. And so this is going to be the last problem that I'm going to be working on for this first part of the video. There's 3 other problems that I do want to work through. And you guys can go ahead and watch that in part 2. All right, so for number 3, we have morphine. So the chemical formula for morphine is C17H19O3N, and it's an organic base. And so once again, we are going to be determining the pH of this solution if this is the concentration of morphine at 25 degrees Celsius. And so the question also told us that the Ka, the ionization constant for the acid, is 6.061 times 10 to the negative 10 at 25 degrees Celsius. And once again, we're after we determine the pH of the solution, we're going to determine the percent ionization, and we're going to determine what the pOH and the concentration of OH is. All right, so the pH, once again, to determine the pH of the solution, we need several things. We need the concentration of H plus at equilibrium. And so to determine the hydrogen ions at equilibrium, we're going to get that by solving for X in the mass action expression. And for us to develop the mass action expression, we need 2 other items. We need the ice table, and we need a balanced chemical equation. Okay, so this is our general solution map. And what we're going to do is we're going to work backwards. So we need to do this first, do this second, do this third, do this fourth, before we can figure out the pH of the solution. All right, so already this problem is telling us that morphine is an organic base. And so once again, whenever you guys are writing a chemical equation for something that is a weak base, you need to add in water as in your reactant. And so here we have C17, H19, O3, N. And once again, I'm going to go ahead and write water as HOH. You guys don't necessarily have to do this. I just want to show how the proton is moved from one side to the other through this transfer of electrons. And so we're going to take this lone pair on this nitrogen. And that lone pair, when it is donated to this hydrogen, it makes a covalent bond between nitrogen and hydrogen. And so this covalent bond between hydrogen and oxygen, those electrons needs to go back to oxygen. Thus, we get a conjugate acid. So this is going to be C17, H19, O3, NH. And since we gained a proton on the nitrogen, we need to write a plus sign. Right? Remember, protons are positive in charge. And so the last item that we get is hydroxide. Okay. So now that we have, let me move the hydroxide over just a little bit. So now that we have our balanced chemical equation, once again, we're just transferring hydrogens from one substance to another. So in terms of balancing the chemical equation, it's already balanced. So we're going to go ahead and develop our ice table. Oops. This is supposed to be liquid. All right, so for our ice table, we need to determine the initial concentration of our organic base, morphine. And in this case, it's going to be 0.0755 molar. So this is going to be 0.0755 molar. Since water is liquid in state, we're just going to go ahead and put a slash all the way through in that column, reminding us that we don't need to incorporate water in our mass action expression and in our equilibrium calculations. If you guys are reading through the problem, there's no indication of what the initial concentration of morphine or the conjugate acid of morphine is, as well as hydroxide. So I'm going to go ahead and blank that out. And so for the change, I'm going to go ahead and look at my equilibrium constant. And so the equilibrium constant that's given to me is Ka. So remember, Ka is the ionization of the acid. And so in the reactant side, is this an acid? No, it's a weak base. It's an organic base. And so you guys always have to be mindful as to whether or not the equilibrium constant for the Ka or Kb, whatever's given to you, matches with the identity of the reactant. And so since morphine is an organic base, that value Ka needs to be Kb, not Ka. And so the ionization of the base must be represented by Kb. And so this lets us know that before we can even assess whether or not morphine is an organic acid or organic base, or I'm sorry, weak acid or weak base, no, I'm sorry. Before we can even assess that morphine is a weak base, we need to determine what the Kb is. And so to determine the Kb, we are going to use another relationship that we discussed a couple of weeks ago. Ka times Kb is equal to Kw. And so Ka, we're just going to go ahead and plug in the number that it gave us, so 6.061 times 10 to the negative 10. Okay. Kb is what we're solving for. Kw is going to be 1.008 times 10 to the negative 14. And this value only holds true at 25 degrees Celsius. Okay. And so since we're at 25 degrees Celsius, we can go ahead and use the 1.008 times 10 to the negative 14. So to solve for Kb, we're just going to divide both of those values. So 1.008 times 10 to the negative 14 over 6.061 times 10 to the negative 10. And so if you plug that into your calculator, the value of Kb is going to be 1.663 times 10 to the negative 5. And once again, our Kb is unitless. And so now that we have the value for the Kb, notice that the magnitude is times 10 to the negative 5. So that's far, far less than 1. So we can go ahead and conclude that morphine is a weak base. And since morphine is a weak base, then that means that the change is going to be minus 1x. And on the product side, since we're consuming morphine, we're going to go ahead and produce the conjugate acid of morphine. And we're also going to be producing hydroxide ions. And so at equilibrium, this is going to be 0.0755 minus x. It's going to be plus x and plus x. And so now that I have my ice table written out correctly, I'm going to go ahead and write the mass action expression. And so I'm just going to go ahead and kind of just jump some steps here. And so the mass action expression is equal to Kb. So the value for Kb was 1.663 times 10 to the negative 5. And then that's equal to x times x, so it's products over reactants, divided by this value. And since my coefficient is 1, 1, 1, and 1, I'm just going to raise everything to the first power. So this is going to be x to the first times this by x to the first over 0.0755 minus x. And so if I reduce my mass action expression, this is going to be x squared over 0.0755 minus x. That's going to be 1.663 times 10 to the negative 5. Once again, we're going to assess whether or not we need to include this x in the denominator. We're going to assess whether or not we're going to include it or exclude it. And we can go ahead and do so by confirming whether or not this statement is true or false. And so the initial concentration is 0.0755. And if you multiply the Kb value times 100, what you guys are going to get is 0.001663. So I'm kind of skipping my steps here. And so is 0.0755 far greater than 0.001663? And the answer is yes. And so we can go ahead and ignore this x in the denominator, thus reducing our calculation to simply this. Okay. And you guys can go ahead and solve for x. So we're going to multiply this to the other side. So we have 1.663 times 10 to the negative 5 times this by 0.0755 equals to x squared. And then we're going to go ahead and take the square root of both sides. And if you plug all this in to your calculator, the value for x is going to be 1.12 times 10 to the negative 3. Okay. And that's going to equal to x. And so now that we've solved for x, or the change, we can go ahead and determine the concentration of H plus at equilibrium. So very similar to the previous problem. If you look at the identity of our reactants and products, so this is morphine, that's not H plus, so we can't use this. This is water, we ignored that completely, so we can't use that. This is the conjugate acid, and so that's not H plus. And once again, this is going to be OH minus. And we know that we can relate the concentration of hydroxide to the concentration of protons at equilibrium by using Kw. And so we're going to go ahead and utilize the equilibrium concentration of the hydroxide ion to figure out the equilibrium concentration of H plus to get our pH. Okay. And so since at equilibrium, OH minus was just defined as X at equilibrium, therefore this value also equals to the molar concentration of hydroxide ion at equilibrium. Okay. And so we can go ahead and determine the pOH first. From the pOH, we can get the pH. And so to determine the pOH, we're going to take the negative log of that answer. And so if you guys plug that in to your calculator, you guys are going to get 2.95078, and there's probably a whole bunch of numbers after. And so since there's 3 Sig Figs in this specific value, when we take the negative log of it, we need to keep 3 places after the decimal. And since the digit past the 0 is the 7, and since 7 is greater than 5, it's going to round that up. So we're going to round that up. And so POH is going to be 2.951. So now that we have the POH, we can solve for the pH. So the pH plus POH is equal to 14. And so here in this case, if we plug in the value for POH, which is 2.951, that equals to 14. Solve for pH by subtracting 2.951 to the other side. We're going to go ahead and get 11.049. And so in this case, if we took this route, we don't necessarily need to solve for the hydrogen ion concentration. And so I wanted to just showcase a different route to get to the POH, or to get to the pH. If you guys wanted to go through the concentration of hydrogen ion at equilibrium, then you would go ahead and use, the concentration of hydrogen ion times this by the concentration of hydroxide ion, and that'll equal to 1.008 times 10 to the negative 14. Okay. And so if you plug in this 1.12 times 10 to the negative 3, you can divide it to the other side and get the concentration of H plus. And then to get the pH, you would just take the negative log of the quotient between 1.008 and 1.12 times 10 to the negative 3 molar. Okay. And so if you guys took this route, you guys might not get the same exact answer that we got here. However, it should be very similar. And the reason why is because of this last significant digit, this 1.008. But it should be very, very similar to what we got here. So the last thing that we're going to solve for is the percent ionization. And remember, that's going to be the change divided by the initial concentration. And so the change in this case is 1.12 times 10 to the negative 3. And then we're going to go ahead and divide that by the initial concentration. So the initial concentration is 0.0755 molar. So 0.0755. Then we're going to go ahead and multiply that by 100. So if you guys plug this into your calculator, let me just fix this, negative 3. If you guys plug that into your calculator, the percent ionization is 1.48%. And so of this initial molar concentration of morphine, only 1.48% of it will ionize water to produce the hydroxide. Cool. And so I'm going to go ahead and stop here for the first part of this video. I'll work through 3 problems showcasing how to calculate the pH for weak acids and weak bases. If you guys want to, and actually let me take that back, I do encourage you to kind of like replay this video and just look at the question. So just scroll to the part in the video where you just see the question, and then work it out on your own, just to see if you can get the same answer that I got. In addition, see if your logic is correct. All right, and so I'll go ahead and stop here, and I'll move on to part 2 of this video, which showcases 3 more examples with varying scenarios for the calculation of monoprotic acids and monoprotic bases.